This time on Mrs. Twoo, we will be learning how to dance. Isn't that right, Mrs. Twoo?
Are you filming?
Yes.
Okay.
Call yourself Mrs. Twoo or I don't film.
Are you filming?
Yes, call yourself Miss Twoo.
No. I'm not going to call myself Mrs. Twoo.
You just did.
I decided I wouldn't, actually. Alright, so my name is Jeff, and today I'm going to try and explain how Lenz's law works. So Lenz's law states that an induced electromotive force always gives rise to a current whose magnetic field opposes the original change in magnetic flux. And it's consistent with Faraday's law of induction, which is kind of a mathematical representation of Lenz's law, or vice versa, depending on how you look at it. So electromotive force here equals negative n times d phi b dt. And phi b, it means electric flux, n means the number of coils in a loop. I'll get to that later. And this negative sign here corroborates with the statement in Lenz's law that the produced magnetic field must oppose the change in magnetic flux. So opposes negative, that's how those two work together. So what exactly is magnetic flux? If you recall, flux is just the amount of something moving through a given surface. So magnetic flux is the amount of a magnetic field going through a surface. The easiest way to visualize this is this way. So if you have a loop with a current running through it, excuse me, that is incorrect. If you have a loop with charges on it, it's a charged loop. And then some sort of surface around it. Alright, that's a pretty crude drawing, but you get the point. So this is some sort of surface around it. We can call it like some sort of net. And this is the charged loop. So if you have a magnetic field running through it, so if you have a magnetic field running through this loop, then there's flux. The magnetic field is going through a given surface. Mathematically, you can represent this by saying magnetic flux equals the integral of the magnetic field divided with the dA, or SA, the surface area, integrated over the entire surface of this net. So in most cases, however, there won't actually be this sort of net. You'll just have to imagine what the surface looks like. Alright, I'm going to demonstrate how Lenz's law works using a galvanometer, a solenoid, and a magnet. And our lab actually has these physical things, but I don't have easy access to that, so this drawing will have to suffice. Alright, a galvanometer is basically just a sensitive ammeter. It detects electric current. A solenoid is a wire that's tightly coiled around a tube. Guys, this is my final. Whatever. You know what? Screw it. I'm gonna hand this in.
Did you see what I did?
No, I don't care.
You have to redo part of it.
Alright, can I stop it here and then we'll resume? Mrs. Twoo, back.
So, excuse me for that little interruption in our video. I'll have to apologize on behalf of those two intruders, as well as my own cameraman, Jeremy Berman.
It's a boy!
Anyways, I think I left off with explaining what a galvanometer was. It's a sensitive ammeter, and it detects electric current. That's all you really need to know about it. A solenoid is a wire that is tightly coiled around a tube, and a magnet is your just regular everyday magnet, north end, south end. You get the picture. So if I were to push this magnet into the solenoid, into this tube here, with the north end going in this way, the needle on the galvanometer will go to the left, And this means that there is negative current flowing through it. In other words, that the current is flowing from negative to positive. So why does this happen? Well, let's take a look at the magnet. Draw a little magnifying glass type thing. So all magnets create a magnetic field that flows from the north end to the south end. So this is basically what the magnetic field lines look like from the magnet. But we don't really care about this entire thing. We really only look at the front end of the magnet here. So for our purposes, we can just say that the magnetic field goes straight out, because we're only really looking at this small part of it. So the magnetic field, here, let me use a different color, that the magnet produces is pointing in this direction. And as the magnet, and therefore the magnetic field, moves into the solenoid, the induced current due to the induced EMF, according to Lenz's law here, must create a magnetic field that points to the right, because it's got to oppose the change in magnetic flux, which is going to the left. So therefore, there must be some sort of magnetic field going in this direction as well. And this magnetic field is created by the current that was induced here. So to find the direction of the current, we now must apply Ampere's law. At its simplest, it states that a wire with a current running through it will produce a magnetic field according to the right-hand rule, and this is the right-hand rule. So if you have a wire with a current running through it, the way you find the magnetic field is you point your thumb in the direction of the wire, of the current, and then you curl your fingers around, and that's the magnetic field. So in this case, you have the magnetic field going into the wall here and out of the wall on this side. So if you could visualize it, point your thumb in the direction of the current, curl your hands. So in this case right here, we must, because the magnetic field must be pointing to the right, the induced current must be traveling along the wire in this direction. So because the magnetic field is going in this direction, the only way that my thumb can be pointing is here. So the magnetic field is going to be traveling along the wire, the current will be traveling along the wire in this direction. And that fits with the galvanometer's reading, that the current flows from negative to positive, because the current's going to flow this way, through the negative to the positive. Pulling the magnet out of the solenoid will do exactly the opposite. The needle will go to the right, meaning that the current flows from positive to negative. And in this case, the change in magnetic flux is to the right, so the produced magnetic field will be pointing to the left. So therefore, the current must flow up the wire, because the magnetic field is this way, so the current is flowing in this direction. So the current goes up the wire around it in this way from positive to negative, and that's why the needle goes to the right. And if you were to flip the magnet and put the south side in, everything would be opposite to the north side, because the magnetic field of the south end points towards it as opposed to out. So I'm sure you can visualize that yourself. So I hope this demonstration helped you understand Lenz's law a little better. Thank you very much.
Kaka!